Okay, so before starting on the windowing, um, understanding why we need to apply a window before we do Fourier analysis, which is a common practice, I thought it's a good time to actually just play around in MATLAB for a while and just see a few things that sort of improves our understanding of the Fourier analysis. So we started doing that in the last class. So we can continue that a little bit. So this is what that program is. I have defined the sampling frequency at 1000 and the duration as 1. And then I have created a time vector which has, in this case, 1000 data points. Okay, from 0 to 0.999 seconds. So if I just plot t, it's just a vector of size 1000 and taking values between 0 and 0.999. Okay, and then I create a sinusoid with a frequency of 100 cycles per second, 2 pi f. So this is frequency, so it's 100 cycles. So if I plot y, it has got 1000 data points and there are 100 cycles in this. And I can just plot t comma y and it will give me, this is the time axis now, 0 to 1, and this is the amplitude. Okay, and here I'm going to plot let me just plot the absolute value first. Plot abs FFTY. So this is how it looks like. There seems to be a peak at around 100, where it's actually at 101. You can just put your cursor there and see x equal to 101. And the reason is that when you do the frequency analysis, so here the x-axis is just the number of data points, and it goes from 1 to 1000. But the first point corresponds to a frequency of 0. And the second point corresponds to the next frequency, which in this case happens to be 1 because the duration is 1. So you have to apply that conversion, and that is done here. This just gives a axis from 0 to 999. So it tells you that the first vector is 0, the second one is 1, the third one is 2, and so on. Okay, if the t was 2 seconds, for example, then the first one would have been 0, the second one would have been half. So it would have said that my frequency resolution is half a hertz, which is 1 by 2, because the time duration is 2 seconds. But nonetheless, in this case, it's 0, 1, 2, 3 up to 999. So if I now plot this, then it sits right at 100. Okay. Now, there are some other interesting things that I want you guys to note. So what's the amplitude here of the Fourier transform? It's 500. How is it related to the amplitude of the sinusoid? What's the amplitude of this sinusoid? Hello? Um, you guys can hear me, right?
Yes.
Yeah. Okay. So sine 2 pi 100t. What's the amplitude of this sinusoid? This is how it looks like. What is it? Okay, so if we express this as a complex exponential, what will that be? Okay, so just so that this is, so when you plot, write something as a sine 2 pi ft, the amplitude is a, and then the frequency is f. Okay, so generic expression or 2 pi ft. If you have a generic expression like this, and this could be sine or whatever, uh, plus phi. Then the amplitude is A, the frequency is F, and the phase offset is phi. This is the formula of a generic sinusoid. When I say sinusoid, it could be a sine or a cosine because they are only shifted by a phase. Okay, so they shifted off by a phase of 90 degrees. So what is the amplitude of this?
1.
It's 1. That's the answer. Okay, so the amplitude doesn't change with time. It's this sinusoidal component that changes, but its amplitude is fixed, and it's actually the sort of like the envelope here. If I reduce the frequency to, let's say, 10 hertz, and plot the signal, you can see that it will touch a 1 and minus 1. Actually, I can just show you all the samples here. Plot. These are all the samples. And if you have many samples per cycle, you can see that you will, go up to 1 and minus 1 because it's densely sampling the underlying sinusoid, which is given by this formula. Okay, so the amplitude here is 1. Now, the question is, if I take its Fourier transform now, so let me just do that. So plot ys abs ffty. Right now it has a peak at 10, which is what it should be because it's a 10 hertz sinusoid. What's the amplitude in this? It's coming out as 500. Okay, so the amplitude here is 1, the amplitude here is 500. Do you guys see what the relationship is between the two? This is related to n, the number of samples that we have. How many samples do we have of the sinusoid? The signal has what length? Y. Come on, guys, say something. This is very unsettling. What's the length of the signal? we looked at y. The length of the signal is 1000. There are 1000 samples because I'm sampling at 1 kilohertz and I'm looking at 1 second. Okay, so the t vector has a length of 1000. So the scaling factor is n by 2 actually. This Fourier transform needs to be divided by n by 2 in order to match the amplitude that you get here. Okay, so I'm going to just write n equal to fs multiplied by t. And now if I plot this, it will be, let me just, yeah, okay, I guess I'll plot it like this. Just defined it here, so. So now you can see that the amplitude here is 1 and in the Fourier transform also, this amplitude here is 1. Okay, is this fine? Does this make sense? Are there any questions? Is the font here big enough? Are you able to see the screen properly? Or is it too small?
No, I think we can see.
Huh? Hello?
We can see properly, I guess.
You can see properly. Okay. So we just had a sinusoid whose amplitude was 1. And the Fourier transform, when it's scaled appropriately, will also give you here the axis in 1 units. Okay, so now what happens when I make the frequency something else like 50? So let me do that. So I'll clear the screen here and I will plot the signal and its Fourier transform. And see the sinusoid is getting faster here and now this has shifted to 50. Okay, now what if I make it 100? So notice that even though the amplitude here appears to be less now because the envelope function is it's a little bit less, and that is because each cycle only has a few samples. Okay, so I'm sampling at 1000, and when my frequency is 100 hertz, each cycle has only 10 points. So it may not catch the peak, but in the frequency domain, it doesn't matter. It's still sitting at 1. If I do it at, let's say, 200, let's see what happens then. Same thing, it's somewhat reduced now, but this is still sitting at 1. How about 400? Oh. So see if this sinusoid, now let me zoom in a little bit to this. So I'll just click here and say x lim 0 to zero point 0.1. So I'm looking at only 100 milliseconds. This is the sampled sinusoid. Okay, and that's because the sampling, the sinusoid, the actual sinusoid has a frequency of 400 hertz. Okay, so each cycle will only have very few terms here. Okay, so 400 hertz means a period of 2.5 milliseconds. Okay, and I am sampling every millisecond. So I'm only catching 2 or 3 points per oscillation. So it looks like a very distorted waveform. You can't really tell whether this is a sinusoid or not. But in the frequency domain, it's still well represented, which means that this level of sampling is actually enough to capture the signal. It's quite interesting, right? Because looking at this, you would think that, hey, it could be maybe a sinusoid or maybe something else. But it's not. In the frequency domain, you can see that it's just perfectly sitting at 400 with an amplitude of 1. See, this waveform looks so odd. Oops, not this one. Here. But the Fourier transform is still perfect. It's sitting at 450 with an amplitude of 1. Okay, but it's all going to fall apart once you hit 500. Let me try 499 and see what happens. Ha! Look at this. Array, here. So this thing doesn't look like a perfect sinusoid at all. In the frequency domain, it is still sitting at 499 at, so okay, here I'll do an XLIM between 490 and 510 hertz. And you can see that it's sitting at 499 and 501, so they are symmetric. So in the frequency domain, it is still showing this as a perfect sinusoid at a frequency of 499. Okay, so I could run a for loop here. So for f, which is my frequency going from 10 hertz with a step of 10 going up to 500, let me create f, a sinusoid with a frequency of f, and I'm going to plot that. And its Fourier transform, and then I'm going to display my frequency, and I'm going to pause, and I'm going to end this for loop. So it's going to keep generating sinusoids every 10 steps, and we will see. After pausing, we will clear this frame. So let me run this for loop. And let's see how this looks. This is 10 hertz. And now when I click 20, 30, 40, 50, and see as your sign, so this thing is always at 1. Okay, even though the waveform here starts to look weirder and weirder. It's always at 1. Okay, and this is really the power of Fourier analysis. When you hit 500, all hell breaks loose. You have now violated the Shannon sampling theorem, here actually it's all zero. Because if you have a sinusoid and you are only taking two samples, okay, so you've got one cycle going from zero to again touching zero and coming back to zero, goes up, comes to zero and goes back and comes to zero. If you are only taking two samples, twice the sampling rate, you'll only catch the zeros. So the sampling theorem says it has to be more than twice, not just twice. So once you have hit 500, all hell has broken loose because you have violated the sampling theorem. But below that, it works. Up to 499, it will work. Even though the waveform kind of looks very odd. This is quite amazing if you think about it, that you are able to capture the sinusoid properly, in the sense that you can always reconstruct the original sinusoid back as long as you are sampling at more than twice its maximum frequency content. Okay, so this is the Shannon sampling theorem in action. Did I say Shannon? Sorry, I meant Nyquist. Sorry, Shannon is a different. Yeah, it's his Nyquist theorem. Uh, okay, guys. Any was that okay? I mean, I'm not hearing much from you guys. Uh, uh, you have to say something. So, was that? Are there any questions on that little demo that we did? Or was it fine? If there are any questions, please ask. If there are no questions, say that it was fine, because otherwise I'm clueless here.
Yeah, it's fine.
Okay, well, thank you. Um, so now let me show you some one more thing, and this is actually going to confuse everyone. I'm going to now also show you the phase of the signal. Okay, before I do that, let me generate another. So we'll get to the sinusoid business in a bit. I'll generate another type of signal. So I'll clear this. Um, so sampling rate is 1000, duration is 1 second, number of points is 1000. It's the product of these two. Made the time vector. I'm going to generate a signal X, which is all zeros. So it's a vector with 1000 zeros. The Fourier transform of this signal is going to be zero, right? Because signal is zero everywhere. So if you remember the formula, it's x e to the power minus j whatever. So if x is zero, everything is zero. But I'm going to say now that the first element is 1. So it's got the first element is 1, everything else is 0. So if I plot t now, plot x now, there's a 1 sitting at the first entry and then it's 0. So this is like a delta function. Okay, I hope you guys can. Okay, let me just do stem x. So it's all zeros, but the first element is 1. So what's the Fourier transform of this signal? Anyone? What's the Fourier transform of a delta function? Okay, so if you remember the formula here and apply the shifting theorem, so let's look at any formula. Um, where's that? Okay, so if you put a delta function at xt, if xt is equal to delta t, here, anywhere for that matter, you will see that when you integrate something with a delta function, the overall thing just takes the value here at wherever the delta function is sitting. Okay, so that's the shifting theorem. So it will just become e to the power minus j k omega naught 0, because this is delta t minus 0. Had it been t minus t naught, it would have become t naught. So this thing is just 1. The Fourier transform of a delta function is a constant. Likewise, the Fourier, this means that if you have sinusoids at all different frequencies and you add them up, you end up getting a delta function. Okay, so let's see that in action now. I have created some sort of a delta function here, and now I ask, so I'm plotting tx here. Sorry, this is still plotting y. Let me clear everything so that there is no y. And I will plot tx now. So it's hard to see. It's the one sitting right here. And I'm going to plot abs FFTY. Sorry, abs FFTX. So see, it's 1 everywhere from 0 to 1000 hertz. It's everywhere it's 1. It's actually quite amazing to think about it, that if you have all these sinusoids together uh, and you just add them up, you actually end up getting a delta function. Okay, and let me now ask, what is the phase of this? So I'm going to do 313 abs FFT. Instead of abs, I'll say angle. So the phase everywhere is 0. This means if for each sinusoid, I just, the phase of that is just 0. So these are actually, sinusoids without any shift, and they all add up to give you 1. Now I'll change this signal and say that x is all zeros, but the second, or let's say the second element is 1. So it's shifted now so that the second element is 1. Okay, so x 1 to 10, if I display, it's now the second element that is 1. What do you think is going to happen to the Fourier amplitude of the Fourier transform? This is now a delta function, but it's shifted by one sample. Okay, I'll wait for an answer. I can't proceed unless you guys at least try to give an answer. This is one of the properties that we had discussed a long time ago. What happens when you shift a signal? Here, this is just a shifted version of the original signal. It's a shift of 1. So somebody has to give an answer here. Time shifting. If x is shifted, what happens to the Fourier transform? So what happens to, okay, this is the answer. This is DTFT. It's a similar one for DFT as well. So what happens to the amplitude of this as compared to the original amplitude? What's the absolute value of this? What's the absolute value of e to the power minus j omega naught, omega n naught? Is anyone trying to give an answer? I can't hear anything. Hello?
Is it 1 again?
Yeah, it's 1, right? It's a e to the power j phi. The amplitude is 1, a is 1, and e to the power j phi, phi is the angle, right? So this is, when you multiply by this, there's no change in the amplitude because the amplitude of this thing is 1. Only there's a change in the phase. Okay, so we had done this a while back when we were talking about, or maybe it was on a board that we had done. We had talked about what, yeah, I don't recall where we had done it, but we had talked about a complex number being written as a e to the power j phi. Any complex number can be written like that. Okay, I don't have it here, but we had done it on the Jamboard. So when you multiply something with a factor like this, there's no change in the amplitude. It remains AK. This one, because this has a magnitude of 1, but there's just a change in the phase. Okay. So that is what happens here. If you now look at the amplitude of this signal, it is again still 1 like before. But now if I plot its phase, it's going to look like this. For a real signal, amplitude is symmetric about the sampling frequency and the phase is antisymmetric. And that is what we are seeing here. Okay, so if xn is real, the amplitude is the same. So the real values of ak and a minus k are the same. This is discrete time Fourier series, but it holds for other transforms as well. But the phase gets flipped, and that is what we are seeing here. If instead of x2, if I had done x5, or let's say x3, and plotted this, it always the amplitude remains 1, but the phase changes faster and faster. And that is because this term here, which is providing that angle, this is just a unit vector with this angle. And as your n naught with this shift is increasing, this angle is changing faster and faster. That's it. Okay, so as you increase k, your angle is now going to shift by a bigger number, 2 pi by n naught, when n naught is large. So I can now run this on a for loop as well. For I, which is the lag now going from 0 to 50, let's say. Let's say I plus 1. So it's all zeros except the I plus 1. So when I is 0, it's the first element. So now if I plot these, and I'll clear this also. So this was first, and as you can see, this, as I move the lag, this signal is now shifting to the right. So one is it's a shifted delta function. Okay, the amplitude will not change, but the phase is just going to become faster and faster like this. Okay, so these are the little things that I was telling you. I can see that, lots of concepts that are still sort of settling in, and there's no easier way than to actually run these kinds of small exercises. They actually teach you guys a lot. It will make a lot of these concepts very clear. And it's only like 10-15 lines of code, hardly anything. Really goes a long way in making you understand how the Fourier transform is working. Okay, so now here's one exercise. I'm going to now also plot. This is what I had done earlier. I'm going to plot the angle also. What do you guys think is going to be the angle? Okay, let's just look at this and then I'll try ask you what this really is. Okay, so sorry, so this is 311, 312, 313. Okay, so it's a 10 hertz sinusoid. You can count 10 cycles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The frequency here is perfect. It's at 10, but look at the phase. It looks so random. Why is that? Why is the Fourier transform looking so odd here? It'll keep happening. Well, you can see there's one region where it seems to be sort of something deterministic here, but all over the place it's zero. Why is that? Anyone? This is a harder question, so think and guess.
Mm, No idea. Yeah, sorry.
Okay, so when we are looking at the Fourier transform, okay, so what's the meaning of this whole exercise here? What I am saying that the original signal that you see on top is obtained by making a sinusoid whose amplitude at let's say whatever 100 hertz is whatever is given here, and then there's a phase of that, and that's your one sinusoid. And if you have all these other sinusoids, you add them together and you get your signal back, right? That's the idea. Now in this case, all these sinusoids have an amplitude of 0. So you create a complex sinusoid whose amplitude is 0 and it has some phase. What is the resultant sinusoid? It's just 0 because the amplitude is 0. So it doesn't matter what the phase is. It could be anything. It wouldn't matter because the amplitude is 0. So it's actually random because it doesn't matter. Because the amplitudes are all 0. It's a e to the power j phi. It doesn't matter what phi is if a is 0.
Yeah. Fine. Correct.
So that is why the only real phase information is here, where it's non-zero. The rest could be anything. Okay, and these are the things to note because lots of analyses that we do on LFP depend on the phase of the LFP signal, but it's of no consequence if the if the amplitude is just too small. Then it's just going to be all random stuff. So let me do a little trick here that will stabilize this whole thing. I'm going to say y is my sinusoid, but I'm going to create another signal x, which is zeros 1 to n, and the first element is 1. This is the delta function that I had talked about. And I'm going to say my y is equal to y plus x. Or even simpler, let me just say that y1 is 1. Remember, if it's a sinusoid, the first element is 0. So instead of that, I'm making the first element as 1. So when I plot y, so when f is 10, y is equal to sinusoid and the first element is 1. So if I now plot this, sorry, f is equal to 10 and now I plot this. It hadn't taken the value. Yeah. So this is my old sinusoid, but the first element has become 1. Okay, so I can do a stem here, which will show each point separately. So it is a sinusoid, but see the first element is 1. See that? Let me just zoom in. The first element is 1 and then it's following a sinusoid. So this is like a sinusoid plus 1 delta function. Now this delta function can be only produced by having a sinusoid. And the delta function representation has a non-zero component at all frequencies, right? It's 1 everywhere. So now if I do this and plot these, you will see that the phases are no longer random. Here it seems that it is 0, but it's actually not 0. It's I'll just do this in on a log scale. So you can see that the values here are not 0. It's a small value, but um, it's actually 1 in this case. So the sinusoid at 10 hertz has much larger value. Okay, so instead of maybe logging, I'll just show you what the amplitude values are. Okay, so abs this, when I do this, so I'll just say Z is equal to this number and just plot some values of Z or show some values of Z. So you can see these are the values of Z and it's a small number, but it's not 0. It's 0.002. So to create this sinusoid plus the delta function, you need some value at each of these sinusoids, at each of these frequencies. Z1 to 20. Here it's a large number at 11, but a small number everywhere. If I didn't have this 0, if I just had the sinusoid, and then I had done the FFT of this, now everything would have been 0 except the 10th entry or the 11th entry in this case. Okay, so when I add this signal here, this little bit here, it has now stabilized the phases properly because the phases cannot be random anymore because the amplitude here is not 0 anymore. It's only when the amplitudes are 0, the phases are random, but otherwise the phases depend on uh, you know uh, will need to be something proper so that the delta function that is sitting here can be represented properly. Okay. And even that this delta function could be very small, could be 10th of the size, it will still hold. So if I run this, Now you can see, now I'm running the same thing, but now it's no longer random. Now you are able to pick out what the actual phase is. And the actual phase, because it's a sinusoid, it's pi by 2. So it is 1 point minus 1.57 in this case, minus pi by 2. Okay, the sinusoid is looking quite similar as before. Now here, if I say, let me just say what the, put this one at a different position, let's say 2. And run this. Now it's the same thing here, and it's a delta function representation of at 2. This is what we had done earlier when we had shifted the delta function to a slightly different value, and now the phases are all going in that way. So this is the linearity of the Fourier transform in action. We are representing a sinusoid as well as a delta function together, and this is the representation in the frequency domain. This is where it all hell breaks loose when it becomes 500. Okay, so please do spend time dealing with these kind of generating these signals, adding values, looking at the absolute value and angle. It will teach you a lot. I mean, it's amazing how much you can learn by doing these little exercises yourself. But it really is time for you guys to do this, okay? Because I'm not hearing much responses, um, and it's going to get harder as we go forward. So you have to spend time doing this. I'm saying this every class almost. It's very important to at least understand the basic Fourier analysis before we can talk about all these other modifications, like applying windows and multi-taper and so on. So we'll start with windowing in the next class. There will be a class on Wednesday because it was a working day, just got shifted to a holiday. It's anyway online, so it doesn't matter. So we will meet again on Wednesday, and I'll start with windowing from then. Until then, I will send you guys this little program by email. But please spend time, high time, it's done, so that you guys are on page, uh, you know, when we start windowing and then multi-tapering and so on. Okay, so I'll finish the class now and stop recording.